What's up, team? Today we're talking altitudes and orthocenters of triangles. Learning target right below. I can find the altitudes of a triangle and where the orthocenter of a triangle is. So an altitude of a triangle is the segment from one vertex to the opposite side or a line containing the opposite side. We'll talk about that caveat here shortly. That intersects at a right angle. So it's going to be perpendicular to the opposite side and it's going through a given vertex. Let's look at an example. We have a generic triangle over here, triangle A, B, C. If we wanted to find one of the altitudes, we could pick any of the three vertices to start at. For simplicity, I'm going to start at vertex A, and I'm going to create a line from vertex A to the opposite side, and it's going to intersect the opposite side at a right angle. So here is an altitude of this triangle, and I'm going to name this point D. So we'd say AD is one of the altitudes of this triangle. Not so bad. It's just perpendicular to one side and goes through the opposite vertex. Okay, let's look at a triangle like this one, DEF. This is where that caveat comes into play, where it says a line containing the opposite side. So if we wanted to find the altitude from E to the opposite side, we need to create a line that is perpendicular to DF, but it also goes through E. Well, EF looks to be horizontal, so if we drew a perpendicular line, it would go straight up. There's nowhere on this line that we can go straight up and intersect point E. So what we're going to do is we're going to start at point E. We're going to draw a line that's perpendicular to DF. In this case, I'm going to try to make it perfectly vertical, and you'll see what happens here. So if we draw a straight line, draw a line straight down, it's kind of funky because it's not actually inside the triangle, but it does intersect a line that contains the opposite side. So that's that chunk in parentheses there. So it creates a right angle with this line. Let's give this a name. Call that X, I guess. So now we have this line EX, this line segment EX, which is one of the altitudes of this triangle DEF. And again, the reason that this is the altitude, even though it's not inside the triangle, is because it's perpendicular to the opposite side. We could not create an altitude or a line segment that was perpendicular to DF and also went through E. So it went through a line that contains DF. In this case, line segment DX contains the opposite side DF. Kind of funky. It's going to take some practice. It's going to take some getting used to stuff that looks like this. This one is a lot more friendly, a lot more easier to grasp. Okay, this last one, we have triangle GHI, and what I'm going to show you here is all three of the altitudes. So again, I'm just sketching them on here. This isn't going to be perfect, but it's going to give you a visual of what we're looking for. So this first one, nice and easy, goes straight down. A, B, C, G, H, I. We're going to have J there. So GJ is one of the altitudes. The next one is going to go H. Okay, there's an altitude, and then IL is going to be one of the altitudes. So all three of the altitudes are drawn on this triangle. The first two, I only drew one of the altitudes. They have three, but I only put one of them on there. This one, it has three, and I placed all three of them on there. One super cool thing that we can recognize about this, of course, I'm imperfect, I just drew these on there, but notice that they all intersect at the same exact spot. If we were to do this using some computer program or something, it would be at the exact same spot. So this spot here, we call a point of concurrency. A point of concurrency. Now, a point of concurrency is a fancy way to say it's any point where more than two lines intersect at the same point. So it doesn't have to be in the context of a triangle. You can have any, say we have four lines there. If they all intersect at the same point, that's a point of concurrency. This particular point of concurrency has a special name, a special relationship that we're going to talk about next. Okay, so the point of concurrency where the altitudes intersect is called the orthocenter. For our final example over here, the orthocenter was right here at point M. For this one, we could find the orthocenter, and oddly enough, the orthocenter is not going to be inside the triangle. That's okay, that happens. This one over here, it's going to look a lot like that last one. So we could find the orthocenter. Not going to take the time to do that right now, though. Next, we are going to get precise with finding the orthocenter using our algebra. Again, this is a sketch. This is an idea of what we're looking at. We're going to get our algebra on next. Okay, here's our big example. Buckle in, it's going to take a little bit of time. I'm going to do my best to make it go as quickly as possible while explaining everything I need to. Feel free to pause, rewind, fast forward, do what you need to understand this stuff. So here's a problem. It looks simple. It looks nice. Find the orthocenter of a triangle with vertices x at 0, 8, y is at 3, 5, and z is at 2, negative 2. So those are the coordinates of the three vertices of the triangle. Our task here is to find the orthocenter. So what we're going to have to do is we're going to have to find the slope of each of these sides. We need the slope of xy. We need the slope of yz. We need the slope of xz. And then we're going to utilize point slope form. So as a reminder, point slope form is right here. It's y minus y1 equals m times x minus x1, where x1, y1 is the value of some point. In this case, it's going to be the opposite vertex. M is going to be the slope, so that's the slope of the line that's perpendicular to the opposite side. And of course, x and y are still x and y. Feel free to pause, write this down, do what you need to do before moving forward. Okay, so the way that I would choose to tackle this, I would do step 1. What we are going to do is we are going to find the equation of the line that goes through vertex x, but goes through vertex x and the opposite side of yz. So I'm just going to write this yz just for kind of a placeholder so I know what I'm seeking. So what I'm going to do is I'm going to find the slope between yz and then the slope of the line that's perpendicular to yz, because that's essential. So to find the slope, we know that slope is delta y over delta x. In this case, it's going to be 5 minus negative 2 over 3 minus 2. 5 minus negative 2 is 7, 3 minus 2 is 1. The slope of this line, yz, is 7. So the perpendicular slope is the opposite reciprocal of 7, which is negative 1 over 7. Cool. Now I have the slope of this line. Let's put it into point slope form. Remember, in point slope form, you need a point and a slope. This is the slope we're going to use. The point that this is going to go through is the opposite vertex. In this case, it's 0, 8. So I'm going to write out the point slope form here. Y minus y1 equals m times x minus x1. And all we need to do now is plug in the pieces. Our m is going to be this negative 1 over 7. That's the perpendicular slope to yz. x1 is going to be the x-coordinate of the vertex. y1 is the y-coordinate of this vertex. So the equation of this line is y minus 8 equals negative 1 over 7 times x minus 0. This is our first of 3 equations. We're going to find all 3 of these, create a system of equations, and see what the value of each of these are. Now, if this was confusing for you, if I went too quick, go back and review. We have stuff. We did slope. We did perpendicular lines. We've studied this before, so I'm not going to take the time to go through that slowly right now. If you need that, feel free to review the other stuff. Okay, our next equation. I set it up ahead of time just because of the sake of time here. We're finding the equation of the line that goes through x, z, and also goes through the vertex y at the point 3, 5. So to find the slope of x, z, I did delta y over delta x. 8 minus negative 2, those are the y values. Difference in the y values, difference in the x's, comes out to be negative 5. Perpendicular to negative 5 is 1 over 5. And then it must go through the point y, which is at 3, 5. So our x1 value is 3, the y1 value is 5, and when we plugged it into point slope form, we got y minus 5 equals 1/5 x minus 3. I encourage you to pause and do what you need to do. I'm going to keep the video going just because of time. Okay, here is the last of the 3 equations that we need to find. It's the equation of the line that goes through the side xy. It's perpendicular to xy, and also goes through the point z. Also goes through the point z. So the slope of the line xy is negative 1, and did the slope formula. Perpendicular to negative 1 is positive 1, and then our x1, y1 is 2, negative 2. Those are the coordinates of z, x1, y sub 1. I plugged them into point slope form. We got y plus 2 equals 1 times x minus 2. Of course, we can simplify a little bit. That'll come. Now, we have these 3 equations. That was hard work. We still have some hard work left. We're going to create a system of equations. So what I'm going to do next is I'm going to erase this whole thing. I'm going to keep the 3 equations, and we're going to solve the system for x and for y. Okay, let me explain what I did here. I took all three of the equations we just found. I didn't change them a bit up top. And then I simplified them. I simplified them by doing the distribution, and I isolated the y on the left-hand side. So this top one, I put a purple box around it, and then I wrote the simplified version in purple. The blue one is the blue one, the red one is the red one. So these are skills that these are things you should be able to do on your own. These are Algebra 1 things. If you're struggling with the algebra, don't feel bad about it. Keep trying. If you're not able to reach this point from these equations here, let me know. We can figure it out together. But these are skills that you should have picked up last year in Algebra 1. And I'm not saying it's easy, but I'm saying these are things that you've learned before. Okay, now what we have here is we have three equations. I've named them equation 1, 2, and 3 for simplicity's sake. And what we're going to do is we are going to set some of these equations equal to one another by doing some substitution. So all of them I've solved for y. That was on purpose because it's going to make our life easy moving forward. Because we know if y equals this stuff and y equals this stuff and y equals this stuff, well, all of those y's are the same exact y because we're trying to find where they all intersect, where the y value is the same. So if y equals this stuff, we can set this stuff equal to x minus 4 or negative 1/7 x plus 8. We get to pick and choose here. So if I'm solving this system of equations, I'm doing some substitution here. I'm going to pick the two easiest ones to work with. In this case, it looks like the purple one and the red one here, so equation 1, equation 3. The reason I didn't choose equation 2 is because there's one more fraction in it. If I can avoid fractions, I'm going to do it. So I'm going to set the right-hand side of equation 1, so that's negative 1/7 x plus 8, equal to the right-hand side of equation number 3. That's x minus 4. And what we're going to do here is solve both sides, we're going to solve this equation for x. This x that we find here is the x-coordinate of our orthocenter. Then we're really close to finishing our problem. So what I would suggest doing here, getting rid of the fraction by multiplying everything by positive 7. Actually, no, let's do negative 7, because right now it's negative 1/7. So we're going to take the entire left side, multiply it by negative 7, and the entire right side, multiply it by negative 7. And what we end up finding is x minus 56 equals negative 7 plus 28. Negative 7x, of course, my mistake. So now we just need to add 7x to both sides, add 56 to both sides, and do a little division. So if I add 7x to both sides, I have 8x minus 56 equals 28. Now add 56 to both sides, 8x equals 84, I believe. Now we just divide both sides by 8, and we learn that x equals, 8 goes into 80 10 times, and so it's going to be 10.5. This is huge. This is the x-coordinate of our orthocenter. It's a huge, huge, huge piece of the puzzle, and we're so close to being done. So now what we need to do is we're going to take this 10.5, and we get to plug it into any of these three equations. Because if this is indeed where the x values of all of these lines meet, or the x value of all these lines meet, then we can plug it into any of these three, and we will get our y coordinate. Again, make it easy on yourself. Pick the easiest one to work with. Equation 1, it's not going to be terrible to work with, but there are some fractions. We'd have to multiply this fraction by 10.5, kind of gross. Same thing here, but then we have this other fraction. This last one, no fractions. Let's take that. So y equals x minus 4, but we have our x value. It's 10.5. So y equals 10.5 minus 4. That means y equals 6.5. So our orthocenter of this triangle XYZ that we started with a few minutes ago up there is at the point 10.5, 6.5. And this is our final answer. The orthocenter is at 10.5, 6.5. So practice problems. Your solution is going to look really simple and neat. It's going to be like this, but it's going to take a lot of work to get there. It took me 2 whiteboards to get there. It should take you a whole page at least. If you look at my notes that I posted on Classroom, it's 2 full pages of work, and I showed a little bit more work than what we talked about here, so you can use that as a reference as well. So when I'm grading your assignment at the end of the week, what I'm trying to say is there should be a lot of work there, because this is labor intensive. This is tough stuff. So take your time. You only have a couple problems, but I want you to do these couple of problems extra well. Okay, let's dive in. Let me know if you have questions.